Hello everyone. Thank you for participating in my presentation. I'm Motohiro Shibaka from DENSO Japan. So DENSO is a automotive tier 1 company in Japan. Our product is, for example, thermal, the air conditioner, and a powertrain electronics control unit, and infotainment navigation system, and of course ADAS system, and so on and so on. So today I'd like to talk about our design approach for mixed criticality system in software-defined vehicle. So this is kind of the application level design method. So unfortunately, it is not talk about hardware or kernel and driver level topics today. So let's go. So this is today's agenda. There is a mainly three parts. The first is what is SDV, and second is SDV technical area and open communities, and finally I talked about our approach for design a mixed criticality system. Okay, so what is the software-defined vehicle? So yeah, SDV stands for software-defined vehicle, as you know. So in the past, the car improved their performance by improving the hardware-centered combustion engine, but in the future, the software will determine the value of the car. And also we can think SDV is a concept and the mechanism of abstracting the vehicle hardware, and software controls the vehicle hardware such as ECU and networks and sensors and actuators through the virtualization platform. So SDV, in other words, so how to separate the application layer and platform layer and hardware. And this is, yes, the development and production of vehicle has shifted from hardware-centric to software-centric. So next, I need to mention the mixed criticality system. So this is a system integrating some components with different safety criticality. So for example, this figure shows some system consists of ADAS application as a critical component, and also this system have a infotainment application as a non-critical system. So these two applications works closely together as one system. So this is a mixed criticality system. So and we are thinking mixed criticality system will be fundamental requirement for SDV/H. So because the evaluation of ECU architecture make it likely that application will interfere with each other. Currently, the isolated many ECU architecture is very common in the car ECU architecture. So we have a specific ECU for a specific domain. For example, ADAS ECU for ADAS application. But near future, this ECU will be consolidated, and zone, this is kind of zone ECU, will be more common. Our next point is hardware abstraction bring a unified design and verification approach and a unified platform for various applications and of course various hardwares. The final point is a new function or new feature are expected from for example, cross-network applications such as some application working with vehicle and cloud, or vehicle to vehicle, or vehicle to something, and so on. Yes, for these reasons, so we must assume mixed criticality system in SDV/H. So what is technical challenges in SDV? So we think it is guaranteed the deterministic behavior of the system. So there is a lot of difficulties. For example, how to handle of the mixed criticality system runtime behavior on the various hardware, and also, for example, how to mix criticality apply orchestration with considering the time critical event. This means which hardware the application will be deployed to. And finally, so how to satisfy the non-critical, non-functional requirement. So more uncertainties have to be taken into account in SDV. so than ever before. For example, some network effect and processor effect and OS operating system effect and so on. Yeah, so the guaranteeing the SDV system deterministic behavior is very important. Okay, now next is SDV technical area and open communities. So this slide shows the technical area required for SDV. So the center diagram, blue character 9, shows the 9 technical area. So we are using these 9 categories to classify the existing SDV related open project. And for example, there are some technologies comes from IT or IoT industry, the microservice or DevOps, digital twin, and so on. And of course, there's a virtualization or some standardization of vehicle interface and vehicle API. And we are focusing on this, the circled 2 area, the mixed criticality and system modeling, to guarantee the system deterministic behavior, as I mentioned last slide, before slide. And yes, as you can see, the wide range SDV technical area cannot be solved by one company alone. So the consortium to develop common standard and common technology is very important to accelerate SDV system development. And the top right logos are major consortium working for SDV. So we have a good keynote about the SOFI in this morning. And also there is Eclipse SDV and Autoza and Kobesa. So this is a very famous SDV consortiums. So yeah, I thought I mentioned about SOFI, but we already have a very good presentation this morning. So yes, everyone knows the SOFI already. Many companies are participating in this open consortium. Of course, DENSO and Linaro. It is difficult to find our logos from this slide, but we are participating. And SOFI is aiming to define software architecture and develop a reference implementation for deployment or orchestration of mixed criticality system. And also they are aiming to develop a platform for seamless cloud to automotive edge software development. So they want to achieve kind of environmental parity. So they want to execute software in same way in any environment, including cloud and automotive edge. And this image, I copied this image from the SOFI materials, and yellow box is SOFI developing items. Maybe it is difficult to read, but they will have some orchestrator located in both the cloud side and the edge side, and also they have some virtualization layer on the edge side. Okay. So yes, now I'd like to explain our design and verification approach for mixed criticality system. So this slide shows the overview of our approach. So our approach consists of 3 key elements. The first is systems engineering. So we want to make some model to specify a safety criteria of each component with using some timing abstractions. Next point is mixed criticality orchestrator. This is kind of runtime to guarantee the system behavior according to the system engineering system models. And this runtime monitors application behavior in runtime to detect some violation of the timing requirement. And finally, the cloud native development is also important. We want to manage the life cycle of application including the cloud to edge. And bottom diagram shows the relationship of these 3 key elements. The first 3, so we start from system engineering to specify a system structure and system timing requirement. And so as next step, we will using the cloud environment to design this system and verification of this system, and also mixed criticality orchestrator here, so guarantee the system behavior according to the timing requirement comes from the system engineering. And after sufficient design verification in cloud side, so the system will be deployed to the real edge ECU. Now, of course, system the behavior is guaranteed here by the mixed criticality orchestrator. Okay. So let's focus on the mixed criticality orchestrator. So as I explained, Sophie also have been developing this mixed criticality aware orchestrator, and their focusing point is next 2 points: the hardware abstraction for critical applications, and also they try to integration of IT industry orchestration tool, Kubernetes, into the automotive edge. And our mixed criticality orchestration solution provides the following capability: provide application level safety envelope for handling the uncertainties, and deterministic scheduling method for handling the real-time requirement of application, and safety safety violations detection at runtime and compile time. So now we are proposing the combination of these two technologies in the Sophie consortium as a realization enabling technology of mixed criticality orchestration. Yes, and this is a technology that enables our solutions. It is called the lingua franca. So lingua franca is a modeling language and runtime to enrich a programming language with ability to specify timed behavior. And this is open source project developed by University California, Berkeley. So you can find more detailed information from these URLs. And this lingua franca have two main features. So first is modeling language for concurrent systems that ensure determinism, eliminating concerns about the threat management or some synchronization. And also lingua franca have a scheduler automatically generated, and this scheduler generated from the lingua franca model and accurately handles time-sensitive event. Lingua franca can integrate complex system with reliability, repeatability, and testability. Okay, let me explain briefly little concretely about lingua franca. So in lingua franca, so reactor represents a functional component that is time encoded, and lingua franca have a deterministic scheduler provides a runtime enables deterministic concurrency. So the left side figure shows a simple one reactor. This is kind of very simple reactor read the data from some sensor. And the blue characters is a lingua franca syntax, and we can specify the trigger timing of this reactor. In this case, so this reactor should run every 100 milliseconds. So we specify the periodic trigger as using the lingua franca syntax. And the dark gray part is application logic. So we can use supported language, for example, C or C++, and so on, to implement the actual application logic. So in this case, it is almost dummy code, just counting up and output the value of counters. Okay, so let's look the more complex. The center diagram is top level reactor. So this looks like a typical model with using the box and connection, but this is just changed the diagram view from the code, similar as a single reactor. And several reactors are connected to form a system. So this sensor reactor output some message, and this message carries not only the data but also the timing of this message internally. And in the runtime, the deterministic scheduler uses this timestamp to decide the execution order of each reactors. Okay, and let's see the center processor reactor. So here is defined the worst case execution time of this reactor. So I specified 100 milliseconds is the worst case execution time of this reactor. Okay, and next, the display reactor have a kind of deadline. So we can specify the deadline from timing the input message is generated to the timing that actually triggered this reactor. So if expected event not triggered within this 100 milliseconds, so some deadline handler invoked by the runtime scheduler. Okay, finally, the lingua franca compiler take this code and generate the application code and generate the deterministic scheduler for some platforms. And in the runtime, deterministic scheduler determines the timing to trigger each reactor and monitors the violation timing requirement. So lingua franca allows us to model and execute deterministic application. Okay, let's look demo video my colleague made. How do I start?
Braking system and a display unit to see the notifications. The periodicity of the sensors can be specified as per the requirement. In the case of the camera, it is 40 milliseconds. In case of the LiDAR, it's 200 milliseconds, just for example. So the processor here checks for the presence of inputs from both these reactors as part of the fusion process. The processor also implements a logical delay equal to the processing time parameter that you define here. This effectively is a logical execution time, allowing you to embed acceptable delays at the reactor level that are taken into account at the downstream reactors as well. Now let's try to compile this. We can do so by invoking the lingua franca compiler, and then once the target code is generated, in this case it will be the C code, we can run the binary, but we encounter a lot of deadline misses. And if we keep a count of them, we'll see that at the display we'll have 3, and at the breaks we have 5. In this case, the reason for those deadline misses can be traced to the minimum delay that we specified here as 50 milliseconds, which is more than the input sensor period of 40 milliseconds. So we are taking more time in processing than the rate at which we are pumping in the data. We can fix this by changing this parameter for the minimum delay to the value less than the input period of the sensor. We can rerun it, and then this time we see that all the deadline misses that we previously encountered are gone. Similarly, at the break, we specify a strong deadline requirement of 10 milliseconds here. This captures the end-to-end physical time delay between the sensor and the break component. And that physical time is equal to the minimum delay that you specify here, plus an additional lag experienced by the time the message gets out to this break reactor at reaction 1. This additional lag encountered around this area could be because of the message propagation delay or execution time at reaction 2 of the processor. In essence, deadline captures the upper bound of delay allowable at the break reactor. Similarly, for the display reactor, we may have a more relaxed deadline in this case 115 milliseconds, given that it is of a lower safety requirement. This is how we can model real-time aspects for our mixed critical applications that can be enforced in runtime as well.
Okay. Okay, next, this slide shows our activity at SOFI consortium. So automated valet parking is AD application is used in the SOFI as their showcase with their development item. But we observe some problems about the deterministic behavior. So this AVP application occasionally exhibit non-deterministic behavior. For example, some order of arriving message is changed occasionally, very low possibility. So now we are proposing the porting of this automated valet parking into the lingua franca. So basically, wrapping this application as a reactor. The bottom diagram shows the ported the lingua franca application. So it can guarantee the deterministic behavior. So yeah, now we are proposing this porting to the SOFI consortium. Okay, finally, I'd like to shift our focus to systems engineering. So system engineering is an approach to design or managing or optimizing the complex system. So it's used widely in aerospace and defense and automotive. So as shown in the figure on the right side, so in the requirement definition process of system engineering, so we define some more comprehensive requirement using a modeling tool or modeling language such as SysML. So and also as a next step in the system or control design process, we often use the Simulink to make control logic. So very lot of modeling language or modeling tool are used in the system engineering. As I explained so far, the lingua franca take a part of this system engineering, but focusing on the modeling the system structure and system timing, so not like a whole systems engineering. So therefore, we are considering this our idea, so integrating lingua franca with the entire system engineering world. So for example, the requirement integration with requirement model or some structure model actually used in our business unit, and some Simulink model as a part of application logic and so on. So to validate and refine a timing requirement in early design phase, so before actual software coding. So we want to reduce the risk of discovering timing issue later, prevent rework. So we want to use the lingua franca to refine the requirement, timing requirement in early design phase as a part of the shift left approach. Okay, this is conclusion. So I should save time for QA session. So that's all for my presentation. So thank you for your attention. Any questions? There's mic here.
Hey, great presentation. Thank you very much. So you showed the lingua franca being used with the OpenAD kits as a part of the SOFI program. Is there any view of doing a deeper integration of lingua franca into DDS itself so that we can monitor timing constraints across all subsystems?
Yes, we are trying to integration with ROS or DDS messaging protocol, and it is including some kind of analysis of the message order and the message arriving timing and so on. Thank you.
You mentioned there is runtime monitoring as well, right? How
Yes.
does that work?
Sorry?
How does that work? The runtime monitoring of...
Runtime monitoring mainly using the message timestamp. So this
Yeah, it's
the
okay.
center around center from the sensor reactor to processor reactor. So this message have a timestamp internally. So then the deterministic scheduler using this timestamp to decide the execution order of reactor.
Okay, but then if that happens during the runtime, that there is a violation, you just log it, I suppose? There's not much you can do at that point, right?
Yes, so we can specify some deadline handler as a error handling. So then the runtime scheduler invoke this deadline handler, so
Some
we can
fault
specify
management.
some code. Yeah.
All right, okay, thank you.
So Casper is looking at this and working on how we're going to integrate with the safety island and fault monitoring.
So Casper mentioned he was doing something around. I did not know it was lingua franca actually.
Yeah.
That's it's quite interesting. Okay, thank you.
Thank you. Okay, finish. I think. Yeah. Maybe last question.
Hi, thanks for your presentation. How do you model or do you take into account scheduling or violations of these rules that come from hardware?
Yes, this is a very good question. Actually, lingua franca only considering the application level. So, but we are trying to transfer this timing requirement to the, for example, time-sensitive networks configuration and so on. But this is under just considering the lingua franca. Yeah, take only the application level monitoring.
Okay, because in the safety engineering in automotive as well, you need to take in the whole implementation of the algorithm into account, which includes both hardware and software. Yeah,
so this kind of integration from the application level timing requirement to the more hardware side is very important. We also thinking. Thank you. Yeah.
Maybe a follow-up question or similar question. I mean, a lot of the safety guarantees that needs to be proven in the automotive world, you need to have the validation path. How much does this help in the, let's say, validation for ASIL B when you need to show the validation part that we have the requirement and the implementation, it includes modeling, and according to the model, things are correct?
Sorry.
Yeah, the validation paper trail that needs to come when you make safety critical systems. You need a lot of paperwork.
Yes. So for each layer, we specify some requirement or actual delay and so on. Yes.
Okay, thank you.
Okay, so thank you for attending. Thank you so much.